Okay, so I'm going to go through alternators here. So this is our next module in machines. So finished DC, now we're on to AC machines. So there are some similarities between the two. So we'll kind of at least hit on those so that we can relate back to what we've already talked about and then show the differences as well. Principal operation going to be very similar. Okay, so converts, think of this like our DC generator. We're converting mechanical energy into electrical energy. So we have to have something that's moving, mechanical energy that's moving either this armature through here or would have to have the field rotating. Either or, we need movement between this conductor and this field, and then we will have a voltage induced in there and generated for us to use. Again, either the field or the armature. As long as one of the two is moving, then we will generate a voltage. They're also called synchronous generators or AC generators. The field is called the field. Okay, again, it's still an electromagnet. We're putting a DC source to this field to create this magnetic field. Okay, and then where the voltage is induced, just like in DC, is the armature. Okay, so those definitions haven't changed. The field is the electromagnet and the armature is where voltage is induced. Okay, to establish relative motion between it, again, it requires two components: the rotor, which is a rotating portion, and the stator, which is stationary. So it says an alternator can be designed with either the armature windings on or the field on the rotor. So we'll talk about the two scenarios here first. We'll talk about the rotating armature alternator. Okay, so this is what we've talked about in DC already, where our field was stationary. We rotated our armature winding through the field and then had voltage generated, and then this is to our load. Okay, so if we have a load hooked up on here, it's going to be drawing current through these armature windings as well. So if we have a small load, okay, we would have a small amount of current going through here. So it's saying these aren't typical of AC generators or alternators because we often have a large amount of current. So if we had a large current through here, that means our armature windings are large. Okay, and it's not common to have a large rotating armature, again, huge armature conductors for a large load rotating through what would be a very small, potentially smaller field winding. Okay, so it's what they're saying is it's difficult to transfer high AC generated voltages and currents to the load through slip rings and brushes. So all these components would have to be rated for an extremely large current if we were going to rotate the armature. So this is rare. Okay, this setup here, it doesn't happen very often, and it says it's limited obviously to lower kVA, which would give us a lower current application. Rotating field is more common. Okay, because what that's going to do is rotate this field, so you can see the north and south here, within the armature winding. So we still have that motion, we still are generating a voltage, but now these armature conductors can be significantly larger, okay, because they're on the stator now, they're not moving around. So this is more common. So the excitation current that creates a magnetic field is now supplied through the brushes and slip rings from an external DC source. And again, the armature is connected directly to the load and is stationary in this case. So advantages of the rotating field as opposed to a rotating armature: the slip rings and brushes are not required to connect to the external load, so they don't have to be rated for that current. The field requires relatively low currents and voltages, so smaller brushes and slip rings, again, because it's just a field that's attached to those now, field current. The rotating field structure can be physically smaller in comparison to the rotating armature, of course, and most of the heat generated comes from the armature windings, which are easier to cool because they're in the stator. Okay, so those are the advantages. Now, rotor design, again, this is the field that's going to be spinning around in there, and it's saying there's two types. So we have our cylindrical and our salient pole. This would be a cylindrical one. Okay, all alternators require a mechanical machine called a prime mover that turns the rotor, so that's where we're getting our movement from again. So this guy's going to be spinning from potentially from a turbine or a combustion engine or something. It says high-speed prime movers such as gas or steam turbines typically drive alternators at 1800 to 3600 RPM. Okay, that's significantly fast. So these alternators require rotors that can be driven at high speed. So cylindrical rotors are used. So it kind of makes sense to me that this would be the high speed one because it's tightly designed. It looks built for speed in some aspects. If this rotated, you could probably not even see it moving at all, right? Unless you looked closely because it's so smooth. It says they usually have 2 to 4 magnetic poles. The windings must be firmly embedded in the slots due to high centrifugal force. Again, so all these windings are deep down inside here because this thing is spinning so fast. Okay, so that's the cylindrical. The other one they talk about is the salient pole. So again, this is still our field spinning around within the armature windings. This is for slower speed prime movers such as combustion engines, water turbines, or electric motors. Salient means projecting or standing out, and each pole of the rotor is easily identifiable. So they're typically shorter in length and larger in diameter. So you can kind of see, obviously these are a little protruding. It's not quite as aerodynamic, I would say, so kind of makes sense that these would be for slower speeds and potentially, again, just safer to operate this at a lower speed. Still, our field winding spinning around here, just the two different types of design. So then your mod talks about frequency. Well, based on the poles and the speed, we can get the expected frequency output of our alternator. Okay, so you're familiar with this formula. We've used it for third year as well too. Again, frequency is cycles per second or measured in hertz. Poles would be the number of poles in the rotor, and the speed in revolutions per minute. Okay, and then our constant of 120 because we're using poles, not pairs of poles. So in this example, again, calculating, we want to be able to manipulate this formula to the best of our abilities so we can potentially solve for poles or speed if we have frequency. So make sure you got that dial. Calculate the generated frequency in hertz of an alternator. Has a 2-pole cylindrical rotor rotating at 3600 RPM, and we just plot those values into this formula and we get 60 hertz. Okay, that's obviously what we're running here in North America, but watch our question bank because we don't always use 60. You could see 50 in there too, so don't get complacent. Your stator assembly. So now stator is where the armature windings, where the voltage is being induced, so voltage that we can use now to hook up to our loads. So the armature winding consists of coils, and they're insulated from each other and from the armature core. Mechanical to electrical conversion happens in the armature winding. Okay, so basically that's where the voltage is being induced. These are all armature windings, but they are laminated and separated from each other as well too. Single phase armature winding connections. So we can have the connections depending on how many windings we have. Again, this is single phase that we're talking about first here, and we'll talk about 3-phase next. Again, these windings can be connected in series or parallel, and that changes the output voltage. Okay, so if I got windings and I got leads brought out, I hook them in parallel and they're both rated at 120 volts. I'm going to get 120 volts out of there, okay, because they're hooked in parallel. If I hook them in series, I'm going to get 240 volt output. Okay, so it depends on how the leads are brought out, how they're connected. So again, just look at here. If I go from line 1 to 1 and to 3, I'm going to have a parallel connection on that side, and then line 2 to 4 and line 2 to 2 and 4. Sorry. That gives me a parallel connection. Here, line 1 goes to 1, 2 and 3 are connected together, and line 2 and 4 get connected. Okay, so that's the difference just between hooking these up in series or parallel. So I just want to show a thing here. I'm just going to get rid of this for a second. Go to my camera so I can kind of just explain some of this winding stuff here, just in regards to what they show in your module as well too. So again, I can have these hooked up in parallel or series, and then we could ask you what the line current is. Okay, so we can compare the two now, obviously, if we're going to set these up both at the same time. So if I got a 3 kVA, 120 volt windings, and I'm going to want to know what the braided line current is based on whether they're hooked in parallel or series. Okay, so here's my series connection, here's my parallel. Okay, so I got an output of 120 here and 240 here. So it just changes when I use my VA. So if this question says I got 3 kVA, so I have 3000 VA, and I'm going to divide that by my, if I'm looking for my current, I'm going to divide it by my voltage of 120 volts, and I'll get a current, line current of, so I go 3 divided by 120, and I get 25 amps. Okay, now because these are in parallel, we know that we would take that current, divide by 2 if I wanted to get the current per winding. So I would see 12.5 amps here and 12.5 amps here. Okay, because the line is 25, but again, these are in parallel, and in parallel I would split my current. Okay, just our rules of series and parallel. So then to compare, I got 3000 VA here again, and we're not using root 3 because these are single phase. Okay, just so we have an understanding of that. I'm going to take my 240 volts because I'm hooked in series, so 3000 divided by 240, and I get 12.5 amps. Okay, so I get 12.5 amps because my voltage is 240 now. So I know in series I would have the same current through each one, so I would still have 12.5 amps here and 12.5 amps here going through the same, because we have a series connection with our windings. Okay, so that's a single phase kind of talk here, and we just want to see that we will see the difference between the single phase and the three phase coming up here as well too. Some of my examples they're just going to be straight out of the module. If they are, I'll make sure and let you guys know that. So it's going to go from current slide here. Okay, so then they talk about your winding turns as well, just kind of the same as what we talked about in DC, where we have basically more windings equals more voltage output. Okay, so number of turns, again, for example, in this one, a 1 stator turn of an alternator generates 1/4 of the voltage of one that would be the same, that would have a 4-turn winding. Okay, so we're really getting 4 times the output. Okay, so just like we talked about in DC. Now, the other thing we're going to talk about are the 3-phase windings, okay, because obviously a lot of our alternators are 3-phase alternators. So again, they're 3 sets of windings that are 120 degrees apart, just like we talked about in third year. They can be connected in Y or delta. Okay, so you have all these examples that they go through in the module. So I'm just going to, again, cut back to my camera here so we can talk about, I can show them in person here. I usually do this stuff on the board, so I'll try and do it on the camera here instead. No. Apparently I drew a giant line through there. Just give me 1 sec. Okay, so we want to look at these 3-phase. Again, this is just kind of more of a review of 3-phase, I guess the shortcuts or the little rules of thumb. So example 1, they're going to get you to get your line and current, your line current and phase current. Example 2 and example 3. Okay, and they're going to do it, and then they're going to talk about multi-winding. So we'll do these ones, just some nice review for us. So first thing I want to do is find my line current and my phase current. Again, I'm going to use my S total formula here. So it's going to be my S total is equal to I line times V line times root 3. Okay, so now we got to make sure and use that root 3 because we're talking about 3-phase. So if I have a kVA and I'm looking for my I line, I'm going to take my V line in this case. So I got 120 on my phase, so I got 208 on the line. So again, because they're hooked in Y, so I get 208 times root 3, and I'll put brackets around that in my calculator. So I go 100 divided by bracket. So I converted that back to VA, not kVA, so 208 times second function root 3, and looks like I get a line current of 277 amps. Again, and then we're going to say, well, what's our 277.6, I guess. What's our phase current? Well, our phase current is the same because we are hooked in Y. Okay, so that's what the winding is going to see. 120 volts, but on my phase level, it's going to see my I phase will be 277.6 amps. Okay, which is a lot, but that's a large alternator with 100 kVA output. That's something that we want to talk about too here. These questions that I'm doing right now, if I'm doing them based on kVA or VA, that's a rated current. Okay, that's what the machine is rated to output. Obviously, if we put load on it, that's what dictates the actual amount of current that's going through it. But just to make sure we have an understanding, if we're using kVA, that's rated. Okay, rated current and voltage. Okay, now this next one is a delta one. So again, line and phase. This time I'm going to use 240. That's my phase voltage, but also in delta is my line voltage times root 3. So I'll find my line current going 75,000 divided by 240 times second function root 3, and I get 180.42 amps. Okay, so that's my line current. Now, I know in delta there's a root 3 relationship between the line and phase. So if I take my 180.42 amps divided by root 3, function of root 3, and I get 104.167 amps. Okay, so that's my phase current. So on my winding here on a phase level, my winding is seeing 240 volts, and it's also seeing 104.167 amps. Okay, so again, just different depending on whether I have them hooked up in Y or delta is going to dictate potentially the the current flow going through it based on our rules for Y and delta. So now the next one talks about multi-windings. Okay, so it's kind of a nice review of Y and delta theory. This one we have multiple windings, so we just want to see what happens per winding when we talk about this scenario. So they're saying that I got 347 on a phase level. Well, if these are hooked in series, I know that's the voltage is going to split. They're going to be exactly the same winding, so they're going to share the voltage evenly. Now, what's the line current and phase current? We can find that out too. So if I got 347 on a phase, that tells me I got a 600 volt line. Okay, that's my V line because that root 3 relationship in Y. So if I want to find my line current now, I take my 225 kVA, I'm going to divide it by 600 times root 3, and I'm going to get my I line. So 225, again I'm putting it in VA, so 225,000 divided by 600 times second function root 3, and I get 216.5 amps. Again, that's my I line, and we know in Y, if that's my line current, that's also my phase current. So I know down here I'm seeing a total phase current of 216.5 amps, and I have a series connection here, so the current that's going through one is also the same. So per winding I'm going to see 216.5 amps and 216.5 amps. Okay, just in case a question said, well, what's the phase current and phase voltage? Well, here's my phase current, 216.5. Here's my phase voltage, 347 volts. But if they ask the same question per winding, what's my current per winding? Well, it's still the same because they're in series, but my voltage is different. So per winding, I'm 173 volts, not 347. That's the phase voltage. Okay, so just watch that. If they're asking you questions per winding, we got to kind of get down a little bit more lower than our normal phase value. Okay, so that's when they're hooked in series. Now I'm going to do a Y here where they're hooked in parallel. Okay, so I draw it a little bit different than they do in the mod, but this just makes it easier for me. So this is saying I got 120 volts on a phase level. That means I got a 208 volt line. Getting that root 3 relationship. between phase voltage and line voltage in Y. So that means I have 120 volts on both these windings because they're in parallel. So I want to find out the line current and the phase current. So I'm going to use my line voltage with my kVA. In this case was 150,000 VAs times 208, or sorry, divided by 208 times root 3. So I get 150 divided by bracket 208 times second function root 3, and I get 416.36 amps. That's my line current. So also in Y is my phase current. So my I phase is also 416.36 amps. So again, if they ask me for my phase voltage, so V phase is 120 volts. I phase is 416.36. Now if I said per winding, well, per winding, yes, my voltage is still 120 because they're in parallel, but my current would actually end up splitting because, again, in a parallel connection, my current's going to, and they're the same windings, so they're going to split it evenly. So I just have to take this phase current divided by 2, and it would be 208.18 amps per winding. Okay, so just some terminology there that's different, again, whether we're hooked up in Y or delta or series or parallel. Okay, this guy here, got a, again, if it's able to be hooked up in series or parallel, we would have two voltages because you could hook them up for a higher low voltage connection. This example doesn't really show that 300, but it's definitely would be available if we have that option. This is saying we have a 600 volt phase voltage, so we have a 600 volt line, again, because this is a delta hookup. So if we go 75,000 divided by 600 times root 3, and we will get our line current, so 75 divided by 600 times root 3, and I get 72.17 amps. Again, that's my line current, so that's I line is 72.17, so I phase is going to be 72.17 divided by root 3, divided by second function root 3, and I get 41.67 amps. So on a phase level, I'm in series here, so again, each one would see 300 volts if I have a 600 volt phase because they're in series, and the current running through each one of these would be my phase current, which would be 41.67 amps. Again, because they're hooked in series. So my I phase is this value, and that's what's going to go through both those windings. Okay, the last one here, I think that's the last one we got from the, yep. So this is the same kind of deal. Forgive my rudimentary drawings here, but we want to get to the point. We're going to have these windings hooked in parallel. Again, and this is right out of your mod, that's where these voltages and values are coming from. So now they're saying on a phase level I got 240. So that shows me that's my lower voltage connection, because if they were connected in series, I'd get the 480. Okay, so that 240/480 is telling me that I have a dual voltage alternator that I could hook up for either. Okay, but in this case we've hooked it up for the low voltage because they're in parallel. So if I want to find out again the phase, the line current, and then find the phase current, I'm going to take the line voltage, which is 240, because line and phase voltage are the same. So I'll take my 200,000 VA divided by my 240 times root 3, and I'll get my I line, so 200 divided by 240 times second function root 3, and I get 481.13 amps. Okay, and again, if I want I phase, I got to get a root 3 relationship because we're in delta. 13 amps divided by root 3. So I just go divided by second function root 3, and I get 277.78 amps. So that's what we're going to see on this phase level now. So I'm seeing per winding 240 volts, because that's the phase value of voltage, and they're in parallel. So what we would do in parallel is take this phase current of 277.78. If I wanted to know per winding, again, I'm going to divide that by 2 to find out what is the current going through each winding, which would be 138.89 amps. Okay, so just watch the terminology on that. They potentially will ask you what's the phase value, what's the value per winding. This is just a really good review of Root 3 information as well too. Okay, so I'm just gonna go back here, finish off on efficiency, and then we'll maybe make another video. So I'm going back to my PowerPoint here. So here's all the connections that I did. Again, they draw them a little differently than I do. I just draw them what makes sense to me. So from current slide, we're going to talk about losses here. So we talked about losses in transformers in third year as well too. We had well, not really mechanical losses in transformers because they don't move, don't have moving parts. But we definitely talked about iron losses, copper losses, okay? And then we have another separate portion of our losses for our alternator in the separately excited field circuit, okay? So in that electromagnet circuit, we have losses in there as well too. So again, our mechanical losses be every rotating alternator has mechanical losses. So we got bearing friction, friction between the brush and slip ring, windage of the rotor, and the power required to drive the built-in cooling fan that could be attached. Okay, so those are the mechanical losses. Then we have iron losses, also called core losses, within the core of the alternator. So these do not change as load on the alternator changes. Okay, the two major iron losses are eddy currents and hysteresis. And we can talk about this in a second. Eddy currents flow within any iron, flow within the iron of any changing magnetic circuit. Magnetic flux induces voltages within that iron. They cause currents to flow. The currents create heat loss, okay, which we record in watts. They are reduced with the use of laminations to create more resistance of the current path. Okay, so that's why our cores are laminated, is because of eddy currents. Hysteresis is the energy it takes for the switching of the magnetic domains in an iron, in the iron introduced to a constant changing magnetic field, and changing because we have alternating voltage and current. So as they flip back and forth, the domains change from north to south all the time. Okay, so there is heat loss based on that. That's why they make the core material out of silicon, so that flipping of domains happens a little easier with less heat loss. Okay, so those are our iron losses. Again, they do not change with load. Copper losses. Heat loss is produced by current in the windings of the alternator, or the copper losses. We do have copper losses in the field too, but let's talk about the armature first. The armature and field have a resistance, and as the load current flows through them, they produce heat loss, or I squared R loss. Okay, so those are watts as well. Unlike iron losses, copper losses do change as the load changes. Okay, so this I here is based on load current. The change in copper loss is to the square of the current draw. Okay, so it's I squared. Looks like my square slid over there. I squared R losses. Okay, just like up here. Alternator efficiency. So we're going to have basically how efficient is our alternator. We're going to have the output over the input, and then we're going to times that by 100, and we'll get our efficiency. So again, they talk about this example here. I'll just go back to the mod so I don't have to rewrite it all. Okay, but basically we've got to think that we have an alternator that's going to output a certain amount of watts for us. Okay, and then there's going to be an input into that machine so that we can have that output that we needed, that rated output, or whatever the output we need to drive our load. Okay, so this is the example that they go through in your module. So some things to just kind of hit on here. The output, okay, is going to be based on our calculation off our rated output here. So we're basically saying that this is, we want to know what it is at rated, okay, the efficiency at this rated load, and power factor of 0.8. So I guess it is an actual hooked up load, but drawing rated current. So we have I just make a little power triangle to show me that, to remind me that the VA here, I can just use power factor, I find the watts. Those are output watts, okay? So power output. Then calculate the total losses, because we want to, first we got to find our line current, okay? Because we have I squared R losses where we need our current. So first thing they're going to do is get you to find your line current, okay? Which is, again, we can see it's a Y connection here with the 347 600 volt. So we know that phase current and line current are the same value. So we have to use root 3 because it's three phase. We get our line current at 96.2. Then we get our copper losses. Again, we're doing this on a per phase level first because that's what the winding resistance that they've given us per phase. And we want to use the same value again because we have a Y connection, so I line and I phase are equal. Then we get our copper losses per phase from our calculation. Then we times it by 3 because there's 3 of them. So we get our total copper losses. Again, this is a portion that varies with load. That's why we're using our load current to find those. Our mechanical losses are based on horsepower. Again, in this example, we use that constant of 746 watts per horsepower to get our wattage for our expected mechanical losses. And then we have our armature copper losses, which we calculated, the mechanical losses, plus the field and iron losses. Again, those iron are fixed. These are all values just that were given to us up here in the question. Okay, there's our 700 there, 500 there. And the 4 horsepower was up there. Okay. So then we get our total losses. So we just add all those losses up, get our total, and we know that our input is equal to our output plus losses. So we take our output, add our losses to it, and that's our input. So kind of the way I look at it is I have this machine, okay, just draw it in pen here, this alternator. I have power going into it, and then I have power coming out of it. Okay, and the power in is larger than the power out. Okay, and that's because I have losses. So again, due to heat, friction, all that thing. So I have power coming in to the alternator. I have losses, then I have my power out, and this would be to my load. Okay, but I'm always going to have larger in than out because the losses are going to be taken out from my in. Okay, so when I use this calculation, find the efficiency, I can see that it's 92.6%. Okay, which is decent efficient, especially for something with moving parts. The second example, the things that are just kind of, it's very similar, but they went at 50% load. So the first thing they did was just half that VA because we're at 50% load, so we got 50% of the VA. Okay, then we still found our wattage, again, which is half. This line current, again, half of that because we halved our VA. Then when we go finish, get all our losses, we're still using our I squared R losses, but because of that squared portion, these losses are actually a quarter of what they were instead of half. Okay, so we had 2,221.2, but because of that squared portion of our current, we see a 25% or a 75% reduction. I guess we only see 25% of what we had. The wattage will be the same. Mechanical losses are the same. The other thing that changed was our field loss because they have copper in them too. So they addressed it here by just changing it to 200. So again, we get all our losses, get our output over our input, and in the mod, they show you this calculation. Okay, the important thing is to notice is that our efficiency went down. Okay, when we were loaded at half of what we were for our full load. It's again because these machines are designed to operate at full load. That's what they're rated to do. So if we put less load on them, they're not going to be as efficient as they would if they had full load on them. Seems kind of crazy, but again, we have to have an understanding that's what they're designed to operate at. Okay, so it says here when the load of the alternator decreased by a factor of 2, armature losses are decreased by a factor of 4. Okay, that's that I squared R. The reduced load decreases the field current and the field losses. Okay, so that's why they went down as well. The iron and core losses remain fixed for any value. Rotational losses remain fixed because the constant rotational speed. So windage and all that kind of stuff. Overall efficiency decreases from full load to half load. And again, it's designed to operate at that. Okay, so we'll stop there and then I'll do the next objective in another video.